Morning, everyone. Am I audible to you guys? মই দেখিছে নে পুৰা ৰঙা হৈ গৈছে। Morning. Am I audible to you guys? Is it yes?
Yes, ma'am.
Okay. Okay. Today I'm not feeling that well. I have broken voice, so just bear with me. Anyway, so today we will start another sorting algorithm, which is quick sort. Quick sort is also based on your divide and conquer approach, and it is similar to merge sort, but there is a specific difference between merge sort and quick sort. Let me share my screen. Okay, so what is quick sort? It is also based on your divide and conquer approach. Okay, so divide and conquer means we are going to divide the array into certain parts. Then we will sort it and we will fix it. What happened in merge sort? In merge sort, we first divided the whole array until we get single element, correct? Once we get the single element, we combine those single elements into one subarrays in a sorted order, and finally we got the final sorted array. But this quick sort is in place sorting algorithm. That means there is no merging involved, but we are going to swap elements inside the array itself. Therefore, it's an in place sorting algorithm. In place means just like your selection, sort, insertion, sort, like those. Now, the key point here is that we need to find a pivot point. Okay, then based on that pivot point, we are going to partition the array into two halves. Okay, there can be different ways to pick your pivot point. Either you can just select the first element as the pivot point, or you can select last element. You can again take a random element as a pivot point, and you can also take median as pivot point. But the most general one is like the last element you take as pivot point, and in some places you can see as the first element. So it doesn't matter which element you take as a pivot point. Okay, so the by default one is that we normally take the last element as a pivot point. Okay, So how we do it? Wait. Yeah. Shit. I forgot my password, I guess. Okay, I forgot the password. Okay, wait up. I just stopped sharing for a while. A pure nonsense. Okay, let me share my screen again. Okay. Hey, Pale. So what happened in quick sort? Suppose I just have an array here. Five, three, and 4. Okay. Suppose this is an array and we have 5, 6, 7. We have 8 elements in this array A. Okay. So in this case, I'm going to take the last element as our pivot point. So what is the pivot point here? Element, it's 4. Now we will create a partition. Okay. So based on this pivot point, I'm going to create a partition. What should be the case? I have to make this partition such a way that this pivot point will be suppose in the middle or anywhere. Then all the elements less than your pivot point will be in the left hand side, all less than 4, and all the elements greater than pivot point will be at the right hand side. Wait. Hello. আমাৰ ক্লাছ এটা কৰি আছো, ক্লাছটো কৰি গৈ আছো 11টা। ঠিক আছে, 11টাত গৈ আছো। So all the elements greater than 4 should be in the left hand side, and all the elements greater than 4 will be in the right hand side. This you can also say less than equal to. So isn't it somehow similar to your binary search or binary search tree? In binary search tree, all the elements less than the parent are in left hand side, and all the children greater than your parent should be in the right hand side. So the concept is same. Here you will just take a pivot point, then you will keep all the elements less than the pivot point in the left hand side, and all the elements greater than the pivot point to the right hand side. Okay, so if you have taken like first point as the pivot point, that means 7. That means you have to keep all the elements less than 7 in the left hand side, and all elements greater than 7 should be in the right hand side. So this is the general concept. Okay, so if you do that, what can be the possible thing? What are the elements less than 4? It's 2, 1 and 3, right? And 3, this is 4, and then all elements greater than 4, what, 7, 7, 6, 8 and 5. Okay, now the thing is, this is your pivot point, this is the partition. That means what? This pivot point is already in a sorted place. So this place is already where it's supposed to be. Then we need to sort the two halves. Okay, if I need to sort the two halves, that means what? I'll split these two halves. Okay, so this part will be 2, 1, 3, and this part will become 7, 6, 8, 5. Just remember the order of these elements can be anything. Here I have written 2, 1, 3. It can be 1, 2, 3. It can be 3, 2, 1. And similarly, the order at this side can be anything. It will depend on the program you will use. Okay. So the ordering can be anything in both sides, just that the pivot point will be in the correct place. Once you get this, you will do the partitioning, then you will split it. Just remember, here I have just given you a logical thing, okay? But we are not actually dividing the array. We will do all this stuff inside this array itself, okay? So this split is just logical split or logical partition. Okay, so in this sub-array also, you are going to do the same thing. That means what? I'm going to take 3 as the pivot element. Then again, I'll keep all the elements greater than, all the elements greater than this will be in the right side, and less than 3 will be in the left hand side. But this one is already sorted, right? Because 2, 1 both are small, so no need to do anything. So but anyway, I need to split it because we still have some elements. Okay, 2 and 1. So in this part, 3 is in the correct position. In this part, 4 is in correct position. Now I have 1 and 2. Again, I am going to take this as pivot element. Then we need to do the same process. That means here, this is not in the correct order, correct? 1 is smaller than 2. So I'll keep 1 and 2. Okay, so after that, after sorting, I'm going to do the same thing. That means what? I'll partition it. Partition how? I'll again take the last element as the pivot point, and I'll split it. Now there is no other element, only 1 is left. So I can say after this swapping, 1, 2, 3 is in correct position. Okay, that means suppose this is your correct order, correct element. So 1, 2, 3, 4. These are in correct place after this part. Now we will go back to the right hand side. This sub array is still not that sorted. So what we are going to do? Again, we'll do the same thing. So after doing this only, after doing in the left hand side only, you will go back to this right hand side. Okay, so again here you will take 5 as pivot point. You will keep all the things in this side, but everything is greater than 5. So I'll take 5 here. Suppose 7, 8, sorry, 7, 6, 8. It can be anything anyways. So I'll swap it. So after this, again I'm going to take 8 as this, then I'll keep everything in. Again same process. That means what? I will just keep doing these things recursively. 8 is already big, right? Everything is small. That means what? Again I will split it, again split. So same process we'll keep repeating until we get the sorted array. So that's the main logic here. So what's the point? First, find the pivot point. You can select any pivot point. Then you will keep repeating it. Is this portion clear to everyone? So if this is the case, how we can write it? Suppose programmatically, I can write just suppose quick sort. Here I'll take your array A, and I also need to find the start and end, right? Start and end, I need to know that, because based on that I'll select the pivot point, or anyway I need to know it. Okay, so once I call this quick sort in the whole array, what I'll do, I'll check if start less than equal to end, right? The moment the start and end will be like same, it will keep doing things. What it will keep doing, it is a recursive process, right? So until we just follow up all the elements in the array, I'll just partition it, correct? I will just partition the array. And how will I partition? I'll take start and end, and for that I'll keep it in a index. Okay, suppose this is your piv index. Pivot index, I'm going to get it, because that pivot index will have to find the pivot index, and after pivot index, finding the pivot index only, I can keep all the elements less than pivot element in the left hand side and all greater will be in the right hand side. So after doing the partitioning, I'm going to call the quick sort again in both sides. Correct? After the partition, we have two sides, left and right. So I'm just going to call the same sorting algorithm in both sides. So one part will be A, start, and your, suppose this piv index -1, and the other one will be your quick sort A, then piv index +1, and n. Why it's plus and minus? Suppose this is the array. If it is the last one, this is your pivot element index. So this array will start from start, correct? Start, and this index is the piv -1, right? And for this side, this is the end index, and this is your piv +1, correct? So same thing I'm doing here. So after partitioning it and knowing the piv index, I'll just do quick sort recursive process in both the size. Is it clear to everyone till here? If the process is clear to you guys, yes. Dula said yes. Others? Okay. So now thing is how we are going to do this partition. Okay. How we are going to do this partition. It's a function, right? I am just partitioning the whole array. So how will it work? We have to know that now. Okay. So what happens here? Take the same array maybe. The original array. 17, 1, 6, 8, 5, 3, 4. So this was our main array, correct? So so here what I did first I selected partition or pivot element as our last element, correct? So I can just say this is our last element. I can say suppose our partition doing it A star and N, right? So I am just taking pivot element as our last. So it will be AN, correct? The last element I'm taking as pivot element. So suppose first I'll initially take this. I'll start from the first. I will consider this is our P index. Okay. 0, 1, 2, 3, 4, 5, 6, 7. Now I'll start from the first. That means what? My loop will go from for I equal to what? To start to n minus 1, right? To the whole element. So what here I'm going to do is that I'll check if that AI, suppose this is our AI is less than equal to pivot point or not. So I'll just check if AI is less than equal to pivot or not. So first I'll check this condition. Now this is not less than pivot. This is greater, correct? So I'll move this P here. I'll move this here. So now again I'll check. This is our suppose P index. So I'll check 2 is get less than 4 or not. Okay. Now 2 is less than 4. So what I will do, I'll swap the value 7 and 2. Okay. So after swapping here, the value 2 will come here and 7 will come here, because first it in 7 is not greater than 4, so this index will come a bit second position. Then now I got 2 is less than 4, and since 2 is less than 4, I'll swap these two values, p index value and this one. Okay, so for this portion, this swapping, what will be the case? I'll just swap this value ai and your a p index, suppose. Okay, so after this, anyway, I'm going to increase this p index. I can say p index plus plus, or you can just say p index equal to p index plus 1. Correct. So now after swapping, this one will look like what? 2 comes here, 7 comes here, 1, 6, 8, 5, 3 and 4. Okay, so this swapping done. Now my p index is here. Now 1 is already small. That means what? I will again do the swapping. So after this swapping, 1 will come here, 7 1 come here. So I'll just directly do it here. 1 and 7. Now my p index is here. Now 6 is greater than 4. I won't do anything. Next, 8, it's greater, again it's greater. Now I got 3 is less than your pivot element, correct? So I will swap this value again. Okay, so after swapping, that means 7 will come here and 3 will come here. 3 will come here. That means what? If I do it directly, 3 will come here and 7 will go here. Okay, now see, there is no elements left, right? All elements are greater. Now p index is suppose here, correct? Now 7, everything is greater than 4. So now what I will do, since no element left which is less than 4, I'll just swap the value of this pivot element and this element. So after this, what? The 6 will come here and 4 will come here. 4 and 6. Okay. So now after this swapping, 4 is in correct side. Okay. 4 is in correct side. Now I will do the partitioning. That means I have to follow the same approach in this left hand side and in this right hand side. Again. So this is just your in place. So for this part, I can just write swap a index. Then finally, I'm just swapping it with the n element, right? Once I get the final p index, I'm just swapping it with the last element, which is our pivot point, and we'll just return p index. So this is our partitioning. So is it clear to everyone? First, just find the pivot element, then find the all lesser numbers and just keep swapping, swapping, swapping. And finally, when there is no more less elements, then you will finally get the original p index value and swap the pivot element to this point. This is the case when I have chosen p index to be the last element. Okay, if I choose the first element, the process will be different. And again, if I take the random one, the process will be different. Okay, so can you tell me what will be the complexity of quicksort? The difference between merge sort and is this merge sort? Okay, yeah, that's correct. And log n in average and best case. So can you tell me how? Okay, your answer is correct, but can you tell me how? N for searching and log n for arranging. Kind of correct, but if you even see this piece of code for partitioning, suppose, what will be the total time complexity? Suppose this one will take some constant time, this one will again take constant time. Again, this inside this whole for loop, this will take a constant time, right? But this loop will run for n times. If you remember our previous classes, if you have one for loop, normally your complexity is just on, correct? Or you can say tn, your time complexity is a, and maybe some constant will be there for this whole partition, correct? So for this partition algorithm, your complexity is on, but now in this case, this is the main program, right? Before partitioning. So partitioning is taking like uh, on times, or you can just say a n plus b times. Now you have to find the complexity for this quick sort. Now the thing is, the complexity of quick sort will depend on the choice of your pivot point. Okay, in the best case, what you are going to do, you are just going to divide all the elements into half, right? Best case, when it will be the best case, when your pivot element will be just in the middle. That means in both sub arrays you will get equal amount of numbers. Okay, so in best case or your average case, you can say for these types it will be log n for both cases, because it will just look like your tree thing. Okay, so suppose just think it as a tree. First you had n elements, correct? Then every time you are going to divide into some halves. So suppose this will be binary search tree. Pivot is 2, for example, and this is greater than 2. Remember, in binary search tree, if we keep going for any tree, our height is log n. Correct? Yeah. Height of tree is log n. And there is n number, therefore it's n log n. And but in case of worst case, when this worst case scenario occurs, when we will encounter the most unbalanced partition possible. Okay, when it will be unbalanced partition, remember, in one cases I saw I saw everything is just sorted in one side. Suppose in this case, if I take 8, so everything is already small, and if I partition, there won't be any left side. There will be everything in right side. So that is your unfavorable or unbalanced condition. That means everything will be either in left side or in the right side. So at that time, you are just going to divide the tree into n minus 1 and all. That is my tree. Okay, yeah. In this case, you are just going to divide it to first, suppose n, next you just divide into n by 2, in the next phase n by 4, and so on. So finally you get log n. If it is unbalanced, that means what? In one side you will get like whole n, and in one side n minus 1, sorry, there won't be any element. Everything is sorted. Again, anyway, you need to call the array. So next time there will be n minus 2 elements and in one side 0, or it can be in either way. So in every time our number of comparison will be n minus 1, n minus 2 and on. So this is your arithmetic expression, right? N into n minus 1 plus n minus 2 and so on. So finally you get n into n minus 1 divided by 2. So for this case your complexity is O(n) square. That's why the worst case complexity for quicksort is O(n) square. But for the best case and this one is log n, because in both sides partitioning will have equal number of elements. So, but you can avoid this worst case when if you take means if you take the pivot element randomly. Okay, in one cases I saw I took element as the last element as pivot point. In somewhere you can take first element as the pivot element. But if you keep randomizing the selection of pivot point, then you can just avoid this worst case, and every time you will just get average or base case, which is n log n. Okay. Is this clear to everyone? The space complexity will also be log n in case of average space complexity. Okay, but in worst case, if you go to the worst case time complexity, then your space complexity will also be O(n). Okay, because in worst case we need to just recursively call like n number of times every unsorted array. Divide and conquer. So here also we just partition in the last one. See here you can see the worst case. Why? In this part everything is in the left hand side and there is nothing in the right hand side. Again same case, left hand side, right hand side is completely empty. So this is unbalanced one. Okay, so to avoid this one you can just randomly select any number as your pivot point, then you just recursively um, do the partitioning and call it. Okay, I just showed second pointer how we do swapping. After that we will do, so yeah, worst case is O(n) square, base case space complexity is log n. So is it clear to everyone? Quick sort. So quicksort is very popular one. This is faster than any other sorting algorithm. That's why in most of the applications people use quicksort. Yeah, we can see that worst case complexity is O(n) square, which is higher than any of the other sorting algorithm. But the main point is that we can avoid this situation. Worst case, Here we can always avoid because we can randomly select any number as pivot point, and according to our convenience we can do the partitioning and keep both sides balanced. That's why quicksort is used by most of the known applications, starting from like commercial computation, suppose used in various government and private organization to sort their data. Data can be like any account data or anything, any sorting element, they will use quick sort because it's faster than anything. Even its name said it's quick sort. Okay, and mainly for the numerical computations we use like priority queue, right? For the priority queues, again, if we want to sort something accurately, quick sort is used. So that is all about your quick sort. I hope it's clear to everyone and how we find the complexity, correct? Okay, everyone. Only Dular is saying yes, ma'am. Okay, ma'am. Okay, so when we will do it in our lab class, again the program will be different for different pivot points. So based on the pivot point, your program will change. Mainly the partitioning thing, but swapping thing will remain same. Okay, okay. If yes, then I just end the class here. I'm sharing. I take attendance. Okay, thank you everyone.